There we go. All right, so we left off last time, and you should, what you'd be getting out of this. We're trying to define decidability in a practical way, understand what that means, so that we have something to compare to when we get to undecidable problems. So the ones that we can, I guess for each one of these, you should have a justification for why it is plausible, reasonable to conclude it. So we started off last time, and you should be aware of the notation that we're using. Acceptance of a language by a DFA is what that shorthand means. And these are decidable languages that we're talking about. So we got partway through, a couple more to do. And so what would be, how would you be able to justify a conclusion that, yes, I can tell whether this language is accepted by a DFA? We kind of fall back on the idea of the Turing machine being able to, I'm sorry, the, let me rephrase that. Acceptance by a DFA given a DFA and a string. It will stop with accept or reject. So how could we justify a conclusion that this is true? Well, if we have a DFA and we feed a string into it, is it guaranteed to stop? We have a DFA, we give it a string, it can't be an erroneous string. So we're not allowing, it has to be over the alphabet, right? So it has to be within the parameters of that the machine could accept it. So will a DFA always stop, I guess, is what we're asking. You give it a string that's within its, made up of characters from its alphabet. The answer is yes. So how could we do the check on given a see how he so this problem, he defines it as given a DFA B and a string W. B is a DFA that accepts input string. So if this is the problem, how could we build a Turing machine that would decide this for us? Well, the justification or the way that we would build a Turing machine is simply to simulate or emulate the processing of that Turing machine. So there's a reason behind doing that DFA, NFA implementation that you did as a program, right? Basically, we can make a Turing machine that would do just what your program did. You go through, trace the steps, and identify, did it end up in an accepting state or did it end up in a non-accepting state after processing this string? So, short answer to all of that is, what's justification that acceptance by a DFA is decidable? Basically, simulate the DFA on the Turing machine. So these are all in the context of we're feeding something into a Turing machine, and remember what are the choices between the two major things that a Turing machine can do, right? A recognizer, oops, and a decider. So the decider always stops with accept or reject, right? And what about a recognizer? Recognizer actually has more possibilities, right? A recognizer will, it is guaranteed that if a string is in the language, the recognizer will stop with accept.
Recognizer doesn't have to stop.
Yeah. But it could reject or loop if the string we feed it is not in the language. So the recognizer could keep running forever, but we never quite know how long it might take for it to stop and find that the string is in the language, or reject it if it's not in the language. So the decider always stops, and that's the key here, is that we can, so how would we build, what we're really asking with each of these, I'm saying to justify it, how would we build a TM that would do this, right? That a decider TM. So we're guaranteed by simulating the DFA because the DFA would stop. When does the DFA stop? When it gets to the end of the input, right? We're guaranteed that the DFA does one move for every single input character. So you give it a finite input string, it will go through a finite number of steps, and it will either end up in an accept state or a reject state. So that's just how it's built. If we simulate the DFA on the TM, it will decide that question. And then, so we went through a few of these. The next one is acceptance by an NFA. So I'm not going to go through all of these on the board on the board in detail. Acceptance by DFA is, these are all decidable. Acceptance by an NFA, how can you justify that? Well, we have a known stopping algorithm that will, worst case, if we have the code for this, we've got a Turing machine that will do this, we can just convert, right? We can run a conversion algorithm using a Turing machine. It will take that NFA, turn it into a DFA, then we can run it through this one. So we're kind of building that the conversion we know is guaranteed to stop, so we could do the conversion and then just simulate the resulting DFA on here, and that will stop. And similarly, acceptance by a regular expression. Regular expression is convert it to we're chaining off of all those little things that we did, the conversion stuff that we did back a chapter or two ago, where acceptance by regular expression, convert it to a DFA first. And then use the acceptance from DFA Turing machine on it for the regular expression, convert to NFA, and then use this Turing machine, right? So we're trying to, we have some dependency here, but we started with the base of, we know we can do this, so let's convert this to a DFA and then run that. Convert this to an NFA, then go through this process, and we end up running a DFA to accept it. And then there are a couple of we can tell with an algorithm whether the language accepted by the DFA is empty. Remember, the DFA is just a graph, essentially. And we can see if any, we can run the TM for TM checks for a path from start to any accept state. Right, so the basic algorithm would be to list off all your states, or go through your start at your start state, look at your transitions, and add to your list all of the states that have a transition to them. And then for each of those new states, add a list of all the states that can be reached from those that aren't already in your list. When you get all done, you're going to have a list of everything that's reachable from the start state, all the nodes. And then we just see, are any of them accept states? And it's basically a connectivity check. If there's a path that exists from, or flip it around, if there's no path that will take you from the start state to an accept state, then the language of the DFA is empty. And I'm going to abbreviate the equivalence of two DFAs. A symmetric difference construction. And so that's a little section in the book here on page 197. Now let's just mention the idea behind that is He shows using a Venn diagram. So we're trying to check for everything that is in, if we're comparing two languages, right? You got the Venn diagram, language A, language B, and we're trying to find everything that's in one but not in the other, and everything that's in this one but not in that one, and then taking the intersection, so the intersection of everything that's in language A and not in B, union with the intersection of what everything that's not in A and is in B. When we get all done with that, we can build that, right? Given the two DFAs, we can build the complement. We did exercises with that. So you can build the complement, you can build the intersection, you can build the union. So by a granted somewhat tedious process, we can go through and we can build the set or symmetric difference DFA. So we build a DFA that represents that symmetric difference, then we check and see if it's empty or not. If it's empty, then that means that the two languages are, or the languages accepted by the two DFAs are the same. So if the symmetric difference is empty, then the two languages are identical. And remember, the reason why we had to do that was you cannot just look at two DFAs and say whether they accept the same language or not, just on the surface, right? The number of DFAs you could build for any one language could be some upper bound, I guess, but you could have a lot of them, right? There is, well, it would be infinite, right? You could, let's see. I'll do it. I need to make it more. So this enforces what odd number of A's, but we could something like this. Be on there. Right. So this one is somewhat redundant, but it will. Can we see that those two are the same language? Right. You have to have at least 1 or 3 or 5 A's. This would enforce 1 or 3 or 5 A's, and then any number of B's scattered around. So these two DFAs are equivalent to each other, but we can't tell just off this, I mean, without running them or playing with them, there's no immediate algorithm to tell you that, other than we can do a construction and see if the resulting DFA that comes through the symmetric difference equation ends up empty, which would mean both of them have exactly the same elements in them. All right, and we could imagine there are lots of different DFAs we could come up with for any one language in general. All right, so that gets us through page 197. The last couple of these are finishing off our list of decidable languages. And then I want to take a little interjection, a little diversion back to looking at our friend the Turing machine and some other kinds of activities we can do with it. To do what we normally would think of as computational stuff. All right, so the additional languages. So you should be familiar with the notation and the idea that kind of a reasonable justification for why a Turing machine could, why or how a Turing machine could solve those things. Well, as you might imagine, acceptance by a string, given a CFG and a string, whether that string can be generated by the CFG. To make this Turing machine into a decider, we need to ensure that the algorithm tries only finitely many derivations. And there's conversion to Chomsky normal form. We did not spend time with that, but that guarantees a maximum derivation of for n terminals in your string, and a maximum of 2n minus 1 steps to any derivation involving that. But in essence, we can implement we know how to implement a PDA that would recognize this language and answer accept or reject. So along with the idea of a proof, what you can't do is try all the possible combinations, right? See if you ever get that string, because it could be infinite. So that doesn't get you to a decider. But we can go with this is acceptable. You can simulate a PDA on the Turing machine, or use Chomsky normal form to the n minus 1 derivation steps. So either one of those will stop. Either one will be a decider, and makes sense, right? Since you can build a machine that will parse, that will just like our PDA did. You give it an input string, it can try the different rules, and it might have to try a few. But if you've got a finite number of rules, it will run through a finite number of steps and eventually determine whether that string can be generated or not. And then empty. Are there any strings that can be generated by this CFG? A CFG could be non-terminating, right? And it could be just an infinite. If you gave it this is a valid give an example of an infinite non-terminating just right. That is a CFG. It is not a particularly useful one, but it meets the rules. There's nothing that says the CFG has to stop. That would give an infinite long string. So this would not be. This is a CFG form. Not a context-free language because it has to stop, right? Yes, you can't do a derivation with this. To tell whether this particular CFG is actually valid or can ever generate anything, we basically do it like we did with the empty DFA. We do a similar thing. Mark the terminals. First, and then find a path to the start. If there is no path to the start, you can't get back to the start symbol, then the CFG, the language defined by the CFG, would be empty, have no members in it. Or in other words, it would be the null set. The language itself has no strings in it. And so we come to a theorem then based on that. Every CFL is decidable. You can tell every context-free language is decidable, meaning if you give it a give a grammar and a string, you can tell whether that string could have been generated by that CFG. Again, that's just, let's see, how is that? I guess that's a, sorry, I'm missing the subtlety here. Ah, the non-deterministic PDA is not. Double check whether our CFGs were, whether our PDAs would stop the way we were building them. Because our PDAs were built off of the CFG. So that's a limiting factor as far as how the PDA was actually built. It wasn't a general purpose PDA by the time we got done with it. So although our wise author.
Is that 2n minus 1 or 2
2n,
-1?
not to the -1, the maximum number of steps. Thanks. So I contend that our construction of the PDA is will stop. But we'll go with this. So when we get done, if we just do the derivations, we can, well, we actually, we can work backwards, right, in the derivation, trying the different ways to generate the terminals. So we can come down to any string that we can if we're given a grammar and an input string, we can decide whether that string can be generated by that CFL or not, by the CFG. Except, right, a context-free language cannot be turned into a DFA. And so we'd have to do the derivations by string substitution. All right, the next, where we go from here, we have, we're adding on to, and I wanted to get this picture in on page 201 before we finish with the undecidable stuff. That is we know that the regular languages are subset of the context-free. And decidable is that these are actually a subset of decidable, and yeah. So there's the hierarchy, the it's off of page 201. So you've got finer and finer subsets. Everything inside here is decidable, which means that what? We'll stop with an accept or reject in a finite length of time. String recognizable is on that edge where it will tell us if the string is in there. We're guaranteed that, but we don't know how long we have to wait. And it may not terminate at all if the string is not in the language. And so that's going to lead us to next, we'll probably hit it next class. I wanted to finish some Turing machine, walking through an example of doing multiplication with the Turing machine, using the idea of the pseudocode to describe what it's going to do. We'll walk through it. And so we'll leave kind of the implementation part of Turing machines after this example that we're going to talk about. All right, so identifying the things that, when you come down to it, the things that are decidable are all the stuff that we've looked at so far. Right? Regular languages, acceptance by DFA, NFA, regular expression, whether they are empty, whether they are two DFAs have the equivalent language, then acceptance of a string by a CFG, and whether that CFG generates no strings at all, whether it's empty set. That makes sense. Everything we've done so far has stopped, been able to stop. All right, so our next big topic will be going into the undecidability side. But prior to that, I've uploaded, I announced a Turing machine example. I'm going to go through that. We'll try to make it. Let's see. Painless is probably overly optimistic. Where we're trying to get is to have, and I'll give let's see, in the homework that is posted, the last problem, I better make sure that's in the assignment. I'm looking for you to have a pseudocode description of how the machine would, I think you're asked to do one or two Turing machines, and the idea is to give the pseudocode describing how that would implement the solution they're asking for. All right, so here is the problem. So let's see if we can, I will not go through it in extreme detail, but we'll kind of walk through what the steps are. Actually, there's a tracing here that goes through the whole thing. But how would you do? Let's harken back for a moment to doing our addition problem from last time. And you know, what did we do? We started with two numbers, something like this, and how did we get the result of doing the addition? So if we're adding 3 plus 2 here, the objective was take two numbers represented in unary form, right? Just using like the number 25 would be 25 ones next to each other. Is that a valid way to represent a number? Sure. Is it a is it a very convenient way? Not so much. Is it a very compact way? Definitely not, right? But does it represent the number? And so we're kind of getting into that whole question of, can I guess I should, let's see, do I want to share this on the meeting or do I want to, yes, I will share my screen for the meeting recording here for the part where I'm talking through the page here, and then I'll switch back when we're on the board. Okay. I think I can hide that. All right, so our guests at home should have this. Remember the addition, it's almost like overly simple, right? I think we started with a pound sign at one end there so we could tell. And so what we did was just, actually we could just go forward as long as we saw ones and we saw the dollar sign, we could turn that into a 1 because we knew that was the separator. And we're just going to add those to get the result of adding those two together. We went to the pound, backed up, made that into a pound. And then the result was we would have had 5 1s next to each other, the result of adding the 3 plus the 2, right? And so kind of from a philosophical standpoint, we might say, well, did we actually do addition or not? Well, did we represent the result of doing the addition? You know, does your calculator, if you have your calculator out on your phone and you do 1 plus 3 equals, it gives you, do we care whether how it got the result? As long as it gets the right result, it gives you a, you know, if you have the kind of calculator I have, it would give you a little 4 image, right? And transform your 1 plus 3, that series of inputs, into a symbol that represents the sum of those. And how do we know if a system is, you know, what are some things we require of the system? Well, we want it, if I'm calling it addition, then it should work with more than just one example, right? If it only works with my 3 plus 2, then we'd say, well, it's not a very robust addition algorithm. But if it will work with any number that I can think of, represented in the way we described, and I get the sum of those two numbers as the result, then effectively we got the result of adding the two numbers together. So now we want to look at a little bit different approach. So all we did was take out one character, but that was sufficient with the representation that we have. Could we do it in, could we represent the number in binary instead and come up with an addition algorithm? Well, sure, right? Your addition algorithm would be like the one that you're familiar with we could imagine a state machine. What do you want to do? 8-bit binary numbers. Then we could take the first 8 bits and add the ones, find the ones column on 2 different numbers, put the result down, right? And we could, again, it's going to be tedious, but we could do that in a different representation. Could we do it in binary coded decimal, which is where each of the digits is represented as a digit, not as the, let's say an ASCII digit rather than the number itself, right? So the symbol for that digit. Could we do that? Yeah, we could do that. It would be more complicated, right? But what I'm trying to get is your buy-in belief that, okay, we're doing a really super simple representation. It's not very efficient, but we could do better. We could do something different. and still get results. We could have a lookup table located way off somewhere on that infinite tape that would convert our ones into, right? Could we convert our resulting number if we got 111 plus 11, and that came out to be 5? Could we turn that into the digit 5 in ASCII? Yeah, we could use that number as an index into a table, right? So there's lots of things we can do. I guess just kind of accepting, yeah, I can say this is actually doing computation, and we're seeing how it's doing it with such a trivial kind of approach that it just moves back and forth across the tape, writing characters. And then if we think about it a little bit more deeply, we go, well, in a sense, that's kind of what my laptop, my expensive desktop computer, my high-powered, however many core computer kind of is doing, right? It's just transforming representations into consistent results. All right, so here's my, I'll go from here. Here's my two numbers to be multiplied together. 2 times 3. What it will do is, so the goal is to determine the product of the first number times the second number and store the result as a unary number again with a pound sign on the left, a series of 1 or more ones, and dollar sign as an end marker. And then at completion, the Turing machine head should be on the leftmost one of the product, and the other content of the tape is not relevant. So we're basically going to build our multiplication by marking off each one of these ones. Every time we mark off a 1 here, we're going to come over and we're going to copy each of however many ones there are here off to the end, and then back up to here, erase that, move over, copy however many ones there are onto the end of the ones that we already had, back up, and when we finally used up all the ones over here, we'll be on that dollar sign, which tells us we're done. We've done all of, we're doing multiplication by a series of additions, right? So we're going to keep writing 3 times. We'll write these 2 ones onto the end, ending them, and then put the appropriate marker. What do we say? We'll put a dollar sign as the end of that, and we'll move the head back to the starting point. So we'll leave that little pound sign in there to as the divider between the numbers we're multiplying together and the product result that we're getting. So I'm not, see if there's any, let's just look through. Here's the kind of format of what the algorithm looks like. And here's the initial configuration. The head is here, and just quickly move through what's going to happen. The first 1 gets erased on the left. Over here there was a 1. We erase that, and then we start writing, going back and forth, writing the copy of the number that we were using. As is, there are millions of different ways you can come up with. This is turning the ones into percent signs to tell where that they've been used up, to tell whether we've seen them or not. Then converts them back to ones, and then goes back and finds another 1 to erase, and keeps going back and forth, copying basically the second number however many times the first number told it to. It was tedious writing this. When we finally get done, we go all the way to the end, writing the $ at the end, and then backing up to the first one, giving us the product here, 6 ones, as advertised. So if you look at this, a question to ask yourself is whether this will work if either or both of the original numbers have value 0. If there are no ones in there, if you just have a head sitting on a $, let's see, the original configuration. If you just had the $ followed by the $ followed by the £, would you get 0 as the right answer and be sitting on it? So that's a little challenge for you to look through. All right. Let's stop sharing. Go. Boom. Boom. And okay. And okay, so this is actually one problem on 3.8, which is I think that's the one that asks for the, come on. They say implementation level description of Turing machines outside the following languages. I'm looking for like pseudocode description there rather than writing the state machine. I'm going to pull it up here. Actually, I guess I better share it over to the meeting. Stand by. That guy. Okay, so okay, so this one is 3.8b. It's an implementation level. Let's see, can I make it bigger? Yeah, there we go. There. W contains twice as many zeros as ones. Okay, so think about well, you should probably look at thinking about all 3 of these, but there's actually a detailed solution. I guess there's an answer for 3.8a in the book, but I am not looking for Turing machine states. I'm just looking for a pseudocode description. So you should be able to give kind of the gist of the approach that it's going to take is doing this and moving back and forth, and then at least a reasonably complete pseudocode description of that. Move left until this, move right until, so like a general approach, and then reasonably detailed. I mean, not short of compilable, but pseudocode that would describe the steps that you would take and how the values would be represented on the. So use kind of without necessarily showing every single. I purposely showed on that example every content of the tape. You don't have to do that, but you should describe what the initial content of the tape is, and then what your steps are. You know, do you have pound signs or dollar signs or percent signs or something to show the ends of it, and then give a reasonable description of how you could tell whether W contains twice as many zeros as ones. Is that language regular language, context-free language? Yes, it is both. Right. So you could actually, and you could make a DFA for this. So don't shortcut and say, oh, okay, here's the DFA for it. So just run the DFA on the Turing machine. I really want you to get the idea of how the Turing machine has to operate with the moving back and forth and looking for symbols and all of that. Just one shot on that particular problem. Yes?
Why did the numbers that turn into percentages turn back into ones?
Otherwise, you'd have to, well, some, let's see, I don't remember if this book shows it. They do, yeah. Like on page 177, I think they're showing putting like a special mark, like a 1 with a dot on it or something like that, to tell, yes, it's a 1, but I've already seen it and marked it off. So you could conceivably treat a percent sign and a 1 at, you know, toggle between them and just use, so you didn't have to erase and rewrite it, but trying to be as clear as possible of what was going on there. But you could come up with other ways of doing it. So there's no one single way of deciding how to mark your place kind of in the process. But it should be fairly straightforward, right? Think about if you're doing it with a PDA, how would you do it? Every time you see a 0, you push it on. Every time you see a 1, you pop it off, right? And so that would eventually, if they were equal, or every time you see a 0, what is it trying to do? Twice as many zeros as ones. So what should you do? Every time you see a 1, push 2 zeros on, something like that. And when you see a 0 pop off, that's the big idea. It's not a perfect solution. All right, so that, keep an eye on the homework due date. We'll have, I think we got a couple more. We got Thanksgiving break coming up, so I'll have to try to work around that. I do try to keep from any, let's see, we don't have any exams coming up, so I'll try to move the, keep the homework around the end of the semester. So I mean, keep Thanksgiving break open, so it actually is something like a break, so that you can do all those other projects that you haven't gotten to yet. All right, we'll call it for today.
Hey,
with undecidability, I hear a voice.
oh, my bad. I was gonna say for the homework, that the PDF you published isn't visible to us yet. If you can publish that, like we can click it, but it says it's locked.
Oh, it may be because, let's see. Okay, I'll double check that for you.
Cool, thank you.
Thanks. Thanks for pointing that out.
No problem.
All right, I'll double check that right now. And we'll see you Wednesday. And our next topic will be in the Chapter 4 undecidability, starting at page 201.